In this comprehensive course on algorithmic trading, you will learn about 3 cutting-edge trading strategies to enhance your financial toolkit. Lachazar teaches this course. He is an experienced quantitative researcher and data scientist. In the first module, you'll explore the unsupervised learning trading strategy, utilizing SP500 stocks data to master features, indicators, and portfolio optimization. Next, you'll leverage the power of social media with the Twitter sentiment investing strategy, ranking NASDAQ stocks based on engagement and evaluating performance against the QQQ return. Lastly, the intraday strategy will introduce you to the GARCH model, combining it with technical indicators to capture both daily and intraday signals for potential lucrative positions.
Hello and welcome to this free Codecamp course on algorithmic trading, machine learning and quant strategies with Python. My name is Lachazar and I'll be your instructor throughout the course. And in this course we are going to develop 3 big quantitative projects from start to end. And the course overview will be the following. First, we are going to talk about algorithmic trading basics. Then we're going to talk about machine learning in trading, some obstacles and challenges we may face while using machine learning in trading. Then we are going to develop the first project, which will be an unsupervised learning trading strategy using stocks from S&P 500. The next project will be Twitter sentiment, and it will be using data from NASDAQ 100 stocks. And the third one would be focusing on one asset. It will be an intraday strategy using a GARCH model to predict the volatility. It would use simulated data. And after that, we are going to have a quick wrap up, and with that, we'll finish the tutorial. But before we continue, I would like to mention that this tutorial should not be construed as a financial advice. It is for educational and entertainment purposes only. We are going to develop some concepts and come up with strategies in the end, but it's not a financial advice and you shouldn't make any decisions based on it. As well, for this course, I would assume that you have at least some Python knowledge and understanding, because down the road we'll deal with some complex problems. And if you're new to Python, you may get bogged down. Nevertheless, you learn some very interesting concepts. So stay along and let's get into it. Okay, algorithmic trading basics. So what is algorithmic trading? It is trading on predefined set of rules which are combined into a strategy or a system. It is developed by a programming language and it is run by the computer. It can be used for both manual and automated trading. By manual, what I mean is that you may have a screener which comes up with a set of stocks you want to trade on a given day, or you may have an algorithmic strategy which is developed into an alert system, and whenever the conditions are triggered, you get an alert, but you execute it manually. On the other hand, you may have a completely automated complex system which does a lot of calculation, comes up with positions and sizing, and then executes the trade automatically. Okay, so what is the role of Python in algorithmic trading? Python is the most popular language used in algorithmic trading, quantitative finance and data science, and this is mainly due to the vast amount of libraries that are developed in Python, as well the ease of use of Python. It is mainly used for data pipelines, research, backtesting strategies, as well it can be used to automate strategies, but Python is a slow language and it can be used to automate low complexity systems. If you have a really high-end system which is really complicated and it needs to execute trades really quickly, you would use Java or C++ for those strategies. Algorithmic trading is a great career opportunity. It's a huge industry. There are a lot of jobs with hedge funds, banks, prop shops, and I've just checked the average yearly base salary for a quant researcher is around $173,000, and this is not including the yearly bonus. It is a great career opportunity, and if you're interested into it, the main things you need to know are Python, you need to know how to backtest strategies, you need to know how to replicate papers, and you need to know machine learning in trading. If you're interested into it, I'll definitely advise you to go for it. Okay, so let's move on and talk a little bit about machine learning in trading and some use cases of machine learning. When we talk about supervised learning, we can use it for signal generation true prediction. For example, we can come up with buy or sell signals on a given stock or a given asset based on predicting the return or the sign of the return of that asset. We can as well use it in risk management. For example, we may use a prediction to determine the position sizing or the weight of a given stock in our portfolio, or to predict where exactly should our stop loss be. And with unsupervised learning, we can use it to extract insights from the data. For example, we can discover patterns, relationships, or structures within the data, for example, clusters, and use it in this way to help our decisions. What are some of the challenges that we may face while trying to apply machine learning in trading? And the first theoretical challenge we may face is the so-called reflexivity feedback loop. And it is referring to the phenomenon that if we, for example, have a machine learning model that is predicting that a stock is going to go up each Friday, and we can form a strategy around to profit from that phenomenon. For example, we are going to buy each Thursday and then sell on Friday to capture that price increase move. If we find this strategy throughout predictions and start trading it, with time, other market participants as well are going to find this market phenomenon and start to exploiting it as well, which would cause the price to start going up on Thursday because everybody is buying now on Thursday instead on Friday. And then this strategy is going to be arbitraged away. So it's this reflexivity feedback loop which is making predictions quite hard. What is most hard while applying machine learning? The most hard thing is to predict returns and predict prices. The next quite hard thing to do is to predict return signs or the direction of a given asset. Is it going to go up or down? The next thing is to predict an economic indicator. For example, it is quite hard to predict non-farm payrolls or weekly jobless claims. And a thing which is not that hard or quite straightforward is to predict the volatility of a given asset. Furthermore, there are some technical challenges like overfitting a model or generalization. Overfitting is that the model is learned the trained data too well and it fails on the test data. And generalization is that the model is not performing the same as on the real data. As well, we may have non-stationarity in our training data and regime shifts, which may ruin the performance of the model. And the last thing is that if we have a really complicated model or a neural network, it is like a black box and we are not able to interpret it correctly. What is the usual workflow process in algorithmic trading and machine learning? That would be to collect and prepare the data, then develop a hypothesis for a strategy. Then you have to code the model and train the model, and then finally backtest the strategy. Okay guys, and some key takeaways from this course. So you learn high-level concepts in quantitative finance, as well practical machine learning in trading. You develop a project from idea to backtest final results. However, we will not automate or execute any trades. We'll just develop a strategy. This course is all about developing a strategy from start to end. So you see the workflow, and this is just a purely research project for educational purposes. I repeat, it should not be construed as any financial advice whatsoever. And with that, we can move to the first project and let's get into it. Okay, so first project is about unsupervised machine learning trading strategy. We're going to use data from S&P 500 stocks. Let's talk a little bit about unsupervised learning in trading. So it involves machine learning techniques to analyze financial data and discover patterns, relationships, and structures within this data without predefined labels or target variable. Unlike supervised learning, where the model is trained to make predictions, unsupervised learning focusing on extracting insights from the data. And some use cases would be clustering, which we are going to use in the first project, dimensionality reduction, anomaly detection, market regime detection, and portfolio optimization. In this project, what we are going to do is first we are going to download all the prices data for all S&P 500 stocks. Then we're going to calculate different technical indicators and features for each stock. Next, we're going to aggregate on a monthly level and filter only the top 150 most liquid stocks from the S&P 500 for each month. Next, we are going to calculate monthly returns for different time horizons to add up to the features. And the next step would be to download the Fama French factors and calculate rolling factor betas for each stock as well to add to the feature set. And at this point, we'll have enough features to fit a model and either make predictions, or in our case, we're going to fit a K-means clustering algorithm, an unsupervised learning model, and we'll use it to group the stocks into similar assets into clusters. And from those clusters, then we'll be able to, for each month, select stocks from a given cluster. And we are going to analyze the clusters and select a particular cluster. And then for each month, we are going to select those stocks within this cluster and form portfolios. However, these portfolios will be optimized. So the weights of the stocks within the portfolio, we're going to find them by using the efficient frontier max Sharpe ratio portfolio weights. And then we're going to form the portfolio, hold for 1 month and rebalance at the end of the month and, form another max Sharpe ratio portfolio. In the end, we'll have the strategy returns for each day, and we will be able to compare our portfolio strategy returns to the S&P 500 returns themselves. Actually, not small limitation is that we're going to use the most recent S&P 500 stocks list, which means that there may be a survivorship bias in this list. This is a huge issue, actually. In reality, you should always backtest strategies using survivorship-free bias data. What is survivorship bias? It is the condition when a stock which have actually went out of the S&P 500 because it was failing is currently not in the list, right? So last year, for example, there was a stock which was failing and going down, down, down. So at some point in December last year, they removed it from S&P 500 and they included a new stock. So if we have made the optimization last November, we could end up with having this stock into our portfolio and actually it affecting our portfolio results. But if we use the most recent S&P 500 symbols list, this stock would not be there. So that's survivorship bias. And for the given project, we are not going to deal with this survivorship bias. So the list we are going to work with has survivorship bias most probably. So yeah, that is a limitation you need to know. In the second project, we are going to develop a Twitter sentiment-based investing strategy. We are going to use the Nasdaq 100 stocks and Twitter sentiment data. What is sentiment investing? This approach focuses on analyzing how people feel about certain stocks, industries, or the overall market. It assumes that the public sentiment can impact stock prices. And for example, if many people are positive about a particular company on Twitter, it might indicate potential for that company's stock to perform well. What we are going to do, first we're going to load the Nasdaq stocks Twitter sentiment data. Then we're going to calculate a quantitative feature of the engagement ratio in Twitter for each stock. After that, we're going to rank all the stocks cross-sectionally for each month and create an equal weight portfolio. In the end, we're going to compare the return of this portfolio to the Nasdaq itself. The second strategy is much smaller than the first strategy. There is no machine learning modeling in this strategy, but the idea here is to show you how alternative or different data, in this case sentiment data, can help us to create a quant feature and then create potential strategy out of it. That's the idea of the second project. And the third project is about an intraday strategy using a GARC model. In this one, we are going to focus on a single asset and we'll be using simulated data. Actually, we'll have daily data and intraday 5-minute data. But what does an intraday strategy means? This approach involves buying and selling financial assets within the same trading day to profit from the short-term price movements. Intraday traders usually use technical analysis, real-time data, and different risk management techniques to make decisions and profit from the strategies. What exactly we're going to do in this project? First, we're going to load the simulated daily data and the simulated 5-minute data. Then we're going to define a function which would fit in a rolling window, a GARC model, to predict 1 day ahead volatility of the asset. After we have that, we'll calculate prediction premium. So we'll predict the volatility and we'll calculate the prediction premium and form a daily signal from it. After we have calculated that, then we'll merge the daily data with the intraday data and calculate intraday technical indicators to form intraday signal. So we will have a daily signal and then on top an intraday signal. So 2 signals. And after we have that, we'll generate position entry and hold until the end of the day. In the end, we're going to calculate the final strategy returns. And this is it for the third project. The idea is to show you how predicting volatility works in intraday strategies. And yeah, with that, guys, we are ready to jump into the first project. So let's get into it. Okay, let's start with the first project, the unsupervised learning trading strategy. But before we continue with the coding, guys, the first step would be for you to pause the video and install all the needed packages for this project. So I prepared a small list up here with all the packages we are going to need for the project. So those are pandas, numpy, matplotlib, stats models, pandas data reader, datetime, yfinance, sklearn, and PyPortfolio Opt. How you can install the packages? You can do it the following way. You can open an Anaconda prompt like that, right? And then just write pip install and the package name, pip install pandas, for example, and do that for each package. That's one way. Another way to do it is through the notebook itself. You can type the following. So pip install and then the package name. So pip install pandas. You do Control Shift and run the cell, and it will install the package. Pause the video, take your time, install all the packages, and let's continue. Okay, so the first step would be to download the S&P 500 constituents prices data. But before that, we'll have to import all the packages we'll use throughout this project. I've already prepared that. Those are all the packages we've just installed, and now we are importing into the Jupyter Notebook. The next step would be to download S&P 500 constituents data. To do that, we can go to this link on Wikipedia, and up here you can see that they have a table containing S&P 500 component stocks, like the symbol, the name of the security, sector, industry, date added as well, so quite some data. So we would like to load this table into our Jupyter Notebook. How we can do that? You just call a pandas read HTML function, and let's see what this would return us. Okay, so this is returning a list containing 2 elements. It looks like 2 data frames. So actually we are interested in the first data frame. Yeah, exactly. We will assign that to an object called S&P 500, and the next step would be to grab this symbol column and extract all the symbols in a list. But before that, I think we would have to make a little cleaning on some of the symbols, because I know that 1 or 2 of the symbols contain a dot, and this would give us an error while we download data from yfinance. So we have to actually replace all dots with a dash, and that would do the job. Next step would be to, just grab list with all the stocks. So yeah, we can just use symbol.unique to list. We will assign that to an object called symbols list, and yeah, that would be our symbols list of all S&P 500 stocks. As we talked in the beginning, this list of stocks is not survivorship bias free, so you need to know that it's quite some of a limitation. All right, so we would like to download the data up to a few days ago. Let's define an object which is end date, and we'll use 2023 September 27th, and the start date would be pandas to date time and date. It would be exactly 8 years ago, so we can just use the end date and we'll subtract 8 years out of it. How we can do that? We just say pandas to date time. We'll convert to date time the end date, and then we'll just subtract pandas date offset and then supply 365 times 8. All right, so now we have the end date, which is 27th of September, which is a string, and the start date would be a timestamp. But that's all right, because we are going to download data from Y-Finance, and this function we use from Y-Finance download function, which takes tickers as an argument. So that would be our symbols list, then start, which would be our start date, and end, which would be our end date. And now this would download all the S&P 500 constituents. If we run it, yeah, it will take some time. All right, so we've downloaded all the data for the S&P 500 stocks. We got it up here. So the next step would be to actually, we'll comment out everything and have this object printed out. As you can see up here, we have the column, and then we have like a multi-indexed column. So first we have the adjusted close, and then we have the adjusted close for each stock. That's not really convenient to work with the whole data frame. At the moment we have 2012 rows and 3018 columns. That's really inefficient. How we can overcome that? We will just use the stack method, which now creates a multi-index. The first level would be the date, and then for each date we have the corresponding 500 stocks, adjusted close, close, high, low. So that's much more convenient. We have 6 columns and almost 1 million rows. So we'll have to change the date frame to be stacked, or actually we can move this method right up here after the download directly. And yeah, now we have our data frame stacked. Next step would be, I would always, when I have a multi-index, I would always want to have labels on both of the index levels. So we say index.names, and we'll assign the new names. So date and ticker, that would be our new multi-index names. As you see, they changed up here. Next step would be to fix the columns a little bit. I would like to fix the column names to be not as titles, but with a lower letters. So that would be df.columns, df.columns.string lower. And that's pretty much it with the downloading and fixing data a little bit before we move to the next step, which would be to start calculating technical indicators and features of all those 503 stocks. Okay, so in the second step, we can start calculating the features and technical indicators for each stock. We are going to calculate the Garmin class volatility, RSI, Bollinger Bands, ATR, MACD, and dollar volume for each stock. Let's first start with the Garmin class volatility. What is Garmin class volatility? It is a volatility measure usually used in forex trading, but it works for stocks as well. It is an approximation to measure the intraday volatility of a given asset. And that is the formula right here. So what do? We define a new column called Garmin class vol, and it would be the following. So log from the high minus log from the low. So that would be, from the low. This whole thing is squared, and then it is divided by 2. Then from this we subtract 2 times log 2 minus 1 multiplied by subtraction of log from the adjusted close, minus log from the open. Again, the whole thing is squared, and we just close another bracket, and that should be it. That should be the Garmin class volatility. Yes, so we now have calculated the Garmin class volatility for each stock. It is calculated on a given row. We don't need to do any fancy calculations for this one. The next one is RSI. So how do we calculate the RSI on each stock? What we're going to do, we are going to group by on the ticker level. So level 1, the multi-index has level 0 and level 1, which is the ticker, level 0 is the date, level 1 is the ticker. So we group by on level 1. Then we are selecting the column, which would be adjusted close, and apply the transform method. And within the transform method, we just apply a lambda function, which would be, so now we have grouped by on each ticker. And what do we want to do? We want to calculate the RSI. To calculate the RSI, we are going to use the pandas_ta package, which is the package to calculate pretty much all of the needed technical indicators. So we use the pandas_ta package, and from the pandas_ we use the RSI function. The RSI function, we have to supply the close price, which would be X. and the length would be 20. And yeah, if we do that, you see now we have the RSI for each stock. How we can double check our work, we select Apple and then RSI, and then we'll plot it. And yeah, as you can see, the RSI goes up and down, so we have worked correctly. The next indicator we would like to calculate is Bollinger Bands, and actually we would want to have the lower band, the middle band, and the upper band, but there is one specification for each indicator. From now on, we would like to normalize and scale the indicator itself. So for the Bollinger Bands, we will supply the log from the close price. First, the function we are going to use is from Panda.ca bbands, and it is taking the close. Just for presentational purposes, we supply a Apple adjusted close, and the length will be 20. When you run this function, it returns 5 columns. So the first one is the lower band, the second one is the middle band, and the third one is the upper band. We have to take this into account, and what we are going to do is pretty much, define a new column, BB low, Bollinger Bands low, and we use the same idea as for the RSI. We are going to group by each ticker, select the adjusted close column, and then we use the transform method, lambda function, and in the lambda function we'll say Panda.ta bbands close would be equal to x. Actually, it will be equal to log of x, so mp log 1p, and then the length would be again 20. When we run that, it will return those 5 columns. What we actually want to do is assign to BB low the first column, which we know it's the lower Bollinger Band. We can say ilog all the rows and the first column. We can repeat the same operation for the mid band and for the upper band. Okay, but this happens when I forget something, and I think I have forgot the second curly bracket to close the curly brackets. Let's see what this would return. Yeah, guys, after you return and calculate something, you can just select all the code you've used and comment it out. Okay, we forgot to change the names. That would be BB mid, and first index, that would be BB high, the second index. Okay, let's run that again and see what we'll get. Awesome, now we have the lower Bollinger Band, middle Bollinger Band, and the upper Bollinger Band, and we have the data scaled and normalized. Next step is to calculate the ATR for each stock. However, the ATR function needs 3 inputs, so 3 columns, not only 1 column. And when we use transform method in pandas, it is actually working when you select only 1 column. It would not work if you have 3 columns as an input. So we would have to use another approach. More specifically, that would be a group by apply. And to do that, we need to define our own custom function to calculate the ATR. We can double check what the ATR function from Pandas.ta requires as input, and it is the high. So we have to supply the high, then we have to supply the low and the close price. Furthermore, we can supply the length, for example, 14. And yeah, it will mess up with the data if we run it like that, because we have to select the data for a given stock. But yeah, you see that it requires 3 columns. So here we are going to define a function called compute ATR. It will take stock data, and up here we will just calculate ATR, which will be pandas.ta.atr. High will be stock data high. Below, then we need the close. The length would be 14. All right, and a little detail we are going to add up here is we are going to normalize the data while we calculate it. So that would be atr.subtract. First, we are going to demean, and then we are going to divide it by the standard deviation. So atr.standard deviation, and yeah, that would be our ATR indicator function. Now we can just say ATR, create a new column called ATR, and group by level 1 again. So we are applying that for each stock. However, up here, when we use the group by apply, we need to add an additional argument to the group by, which is group keys equal to false. because if we don't do that, it will double the date column. So it will return another date column and we'll have a triple multi-index with 2 date columns. We don't want that. So we just say group keys equals to false and then apply this function. And this will now calculate the ATR index normalized for each stock. The next indicator we are going to calculate is the MACD indicator. And for the MACD, we're going to follow the same logic as for the ATR indicator. We're going to define our own custom function to compute the MACD. So it will be called compute MACD. It will take the close price. And up here, we are going to say MACD is equals to pandas ta.macd close equal to close. Length is 20. And then we would like to get the first column, which would be returned. However, in the end, as well, we are going to normalize the data. We are going to demean the series and then we are going to divide by the standard deviation. Why do we do that? Right away, we're normalizing the data because we are going to use it into a machine learning model. We are going to cluster the data. We want to do that straight away and don't think about it later in the future. So here we are going to do again group by level 1, each ticker on each stock, group keys equal to false, and then apply compute MACD. This would calculate the MACD indicator for each stock. All right, we have an error. Why do we have this error? That's quite strange. Oh, okay, I'm sorry. I forgot to add the adjusted close column up here. And this is driving the error. All right, so we would return back a log in the first column. That should be the gas. All right, yeah, now we have the MACD as well, calculated and normalized. As you can see, we have the data looks pretty good so far. The only indicator we are not going to normalize is the RSI, and there is a particular reason for that, but you understand more about it when we come to the clustering part. All of the other indicators we are going to normalize. And the final one is the dollar volume. So we are going to create a new column, dollar volume, which would be equal to the adjusted close multiplied by the volume. However, we may want to actually divide that by 1 million for each stock, because we know that millions of shares are traded each day, and this would make sense. As you can see, now the data looks much better for the dollar volume, right? And that's pretty much it with calculating the first batch of features, our technical indicators. Now we have a really beautiful data frame. For each day, we have all the 500 stocks. We have the close price, high, low, open, volume, Garmin class volatility, RSI, Bollinger Band, ATR, MACD, and the dollar volume for each stock. And we are now ready to move to the next and the third step. In the third step, what we want to do is to aggregate on a monthly level the data and filter the top 150 most liquid stocks for each month. Why do we do that? We do that to reduce training time for any potential machine learning model and experiment with features and strategies. What is my idea here? I would like to aggregate all the indicators. So those 5, I would like to take the end value, the end of the last value for the month, as well as the same for the adjusted close price. And for the dollar volume, I would like to get the average dollar volume for the whole month for each stock. We can start actually, what we can do first is take the data frame, unstack the ticker level. So we'll unstack ticker, and then we're going to select the dollar volume column. And if we run that, we have the dollar volume for each day for each stock now, right? And what we can do is just resample to monthly and take the mean. This should resample to monthly. Now, as you can see, we have a monthly index end of each month, and we have the average dollar volume for the month. What we can do now is just stack it back into a multi-index like that, and we can say to frame to make it a data frame with one column, to frame dollar volume. Beautiful. That would be the first step. However, for the indicators, what we can do is we can follow the same logic, but we need to select the exact columns. Actually, we may create a list of columns, so last calls, and this would be our list of columns for which we want to do the same operation. However, we would use the last method up here instead of mean, and those columns would be C for C in df.columns.unique, and yeah, the first element, C for C in df.columns.unique if C is not in the following columns list. So if the column is not $volume, it is not volume, it is not open, it is not high, low, or close. Pretty much we want to do that only for the technical indicators columns. So for those columns, we don't want to use these columns for our aggregation. We want just we are creating the features data frame in the end, right? We would use the $volume to filter out the most liquid stocks. The $volume would not be featured in our model. As well, neither the volume or open, low, high, close. After we have defined the last columns, we can actually proceed with the next aggregation. We have done the $volume aggregation. The next one would be for df last calls. We are going to unstack. Actually, we are going to unstack before that. So we are going to unstack. We're going to unstack and select those columns, and then resample to monthly, and then just use the last value like that. And again, we're going to stack backwards into a multi-index. Voila. And now what we can do is concat those two together. We can say the following: pandas concat, and that would be axis 1, and boom, we have the $volume, the average $volume, and the last value for adjusted close ATR and other technical indicators for each month. Now we have aggregated the data to monthly level for the features we would need. Actually, what we can add up here is a small drop, and that looks much more beautiful, and we can call that data. And let's visualize what we have. And yeah, that's our data. All right. And that's the first step with the aggregating to a monthly level. The next step would be to calculate the 5-year rolling average $volume for each stock, and then use this aggregated $volume to filter out only the top 150 most liquid stocks for each month. How do we approach that? First, we can start by selecting the $volume like that. So what we can do, select the $volume, unstack the ticker level, and now we can use a rolling function with a window of 5 times 12, so 5 years, and then we can calculate the mean. As you can see, now we have the rolling average mean for each stock, rolling average 5-year $volume for each stock, and again we can just stack backwards. And that's pretty much our $volume column. What we can do now is we can assign it to the $volume column, update it to the 5-year rolling average for each stock. Awesome. After we have that, the next step is to calculate the $volume rank cross-sectionally for each month. How do we do that? We can say data group by level 0 or date. So we can group by on date. For each month, we're going to select the $volume and just rank ascending equal to false. Let's see what this would give us. Ascending. And now, as you can see, we have all the stocks ranked by $volume, and the guys who have the smallest $volume have the highest rank. So we want the top 150, and from here we can pretty much very easily select the stocks which are below 150 for each month, and those would be the top 150 most liquid stocks for each month. After we have selected them, we can just drop the two columns, we can drop the dollar volume and the dollar volume rank because we are not going to need them anymore. Axis equals to 1. And that's pretty much it for our, we can assign that to data. And that's pretty much it with our third step, where now we have aggregated monthly data for all the features we would need, plus the adjusted close price. And we can move on with the next step, the fourth step, and that would be calculating monthly returns for different time horizons and add them as additional features to the ones we already have here. Okay, so let's move to that step. I'll just cut those cells in the middle. All right. Why do we want to calculate the monthly returns for different time horizons and add them to the feature set? Because we may want to capture time series dynamics that reflect, for example, the momentum patterns for each stock. To do that, we can just use the pandas data frame method %_change and supply the different lags. My approach would be to use lags for 1 month, 2 months, 3 months, 6 months, 9 months, and 12 months. That's like 6 different lags to really capture the momentum patterns. How do we approach that? Let's first start by, for example, selecting the Apple stock. I just want to make a little example. So we'll select the Apple stock and let's see what we have here. All right, now we would like to calculate the returns for the following lags for 1 month, 2 months, 3 months, 6 months, 9 months, and 12 months, right? As well, we may want to have an outlier cutoff because we are dealing with a lot of stocks. There will definitely be outlier values in the returns of those stocks. What do we want to do? We want to deal with them by clipping them. What clipping does is that for all values which are above the outlier threshold, they will just be assigned the threshold of that percentile. The cutoff value, we may want to have it as a 0.05, which means the 99.5 percentile. That would be our outlier cutoff. And now what we do is just for each lag, so for lag in lags, for each lag, we are going to create a column which would be the return for the given lag, for the given lag month, right? That would be the column. And then we grab the adjusted close. Then we just do %change lag. So for each lag, we'll calculate the following column, which would calculate the given return. And then we want to deal with the outliers, right? So that would be pipe lambda. So far we have the adjusted close, and then we calculate the return for the given lag, and then we input that into the pipe lambda. X we can clip now. We'll clip the return, and we can clip the lower band. The lower cutoff we'll use X quantile, and we'll supply for the lower cutoff just the outlier cutoff. And for the upper one, we'll supply X quantile 1 minus outlier cutoff. Then we add 1 to the power of 1 divided by the lag, and we subtract 1 in the end. And that should be it, guys. Now we can see that for our Apple stock, which is G, right? We have the 1 month return, 2 months return, 3 months, 6 months, 9 months, 12 months, etc. How we can extend that? We'll just use the same approach we use for the ATR and the MACD indicators. We'll create our own custom function, and then we just use the group by apply methodology for the pandas data frame. So calculate returns. It takes DF, for example, and just move that a little bit, return DF in the end. However, up here we have to change that to DF, this one to DF as well. And that's pretty much it, our function. And now we can say the following: data equals to data.groupby level 1, because we group by on the ticker level, so we can say group by ticker or level 1. Let's say level 1, and then we want group keys to be false, so we don't have two date indexes assigned to the new data frame. So group keys false, then apply. We apply the calculate returns function, and in the end we may want to drop the NA values. And yeah, this would take some time, and yeah, that's pretty much it. I mean, now we have added the return features as well, which we would use to capture momentum patterns for each stock. And that's pretty much it with the fourth step, the calculating the monthly returns for different time horizons. And we can move to the next step, which is really interesting, are actually adding even more features to our data set. That would be to download the Fama French factors, and we're going to calculate the rolling factor beta for each stock in our data. All right, let's move to it. Okay, so in this step, we're going to download the Fama French factors data and calculate the rolling factor betas for each stock in our current data set. So we want to introduce the Fama French data to estimate the exposure of our assets to commonly known risk factors. And we're going to do that using a regression rolling OLS model. The 5 Fama French factors, namely market risk, size, value, profitability, and investment, have been shown to empirically explain asset returns in the past and are commonly used in the asset management industry to assess the risk return profile of different portfolios. So it kind of makes sense to include them in our current feature data set. How we can do that? We can use the Pandas data reader package, which we imported as web. We can use this package to download the Fama French factor models. But before that, we may want to take a look at the data. So we can Google it, Fama French factors, and up here you can find the Canet French data library. Just click on it, and this is the part we are interested in Fama French 5 research factors, 2 times 3, so those 5 factors. That's the data we are interested in. If you scroll down a little bit, you can find the daily data right here. You can download it as TXT or CSV file as well. You can check the details. They have monthly returns and annual returns. We are interested in the monthly returns as our data is already on a monthly level, right? So what we can do is we can say the following: web.datareader, and up here we have to supply the name of the exact factor, so the exact file. So I have prepared that already. That's the name. Then we say Fama French. Then the start date, we want 2010. This is returning a dictionary with 2 keys. The first one is the monthly factors and the second one is the yearly factors. That's awesome. So we want the monthly factors only. And that's the data. We have 164 months up to August 2023. That's pretty good. However, I think we don't, even though the risk-free return is pretty solid right now, it is out of the scope of this tutorial, so we'll just drop it. You say drop rf axis equal to 1, and that's perfect. We can call this assign it to factor data, and yeah, that's our factor data. Let's check the index. The index is monthly. Yeah, all right. So I think we have to fix the index as well, so we can call the pandas to datetime and supply the index. Let's see if this would work. Okay, we have to use to timestamp. All right. Okay, so now we have fixed the index as well. As you can see, now it has the year, the month, and the beginning of month date. However, our data is end of month. That's one thing we have to fix. Another one is that I see that the factors are in percentages, so we would have to divide them by 100. How we can fix that? We can just say resample to monthly and get the last value, which would fix immediately the issue, yeah, with the beginning of month date. Next we can say divide by 100, and that's perfect. We just assign that to factor data. Comment it out. Yeah, next we want to fix the name of the index to be just date, and the next step would be to join with the pretty much join with the 1 month return. Why would we want to do that? Because at the beginning of each month we have the factors, and then we have the return of each stock at the end of the same month. So now we have fixed the date of the factors. We can just join with the end of month return, and then we can regress them and take the beta, right? If the factor is predictive, we have it at the beginning of the month and we will regress it with the return of the end of the month. So we'll get the beta. How we can do that? Factor data, join, and then from our data, we can select the one return column. Let's see what this would give us. That's perfect. Now we can sort the index and just assign it to factor data. What we may want to do here is to double check our work. We can select two stocks, for example, Apple and let's say Microsoft. And we can double check the return. Yeah, the return is different, but the factors stay the same. It looks like we've worked correctly. And we are ready to move to the next step. In this step, we are going to filter out stocks that have less than 10-month data. Why are we doing that? Because we're going to use a rolling window for the regression of around 2 years, 24 months. And stocks that don't have enough data would actually break our function, so we have to remove them from the data set. How we can do that? We can say factor data dot group by level 1 and then just call the size method, and now we can see how many months of data we have for each stock. Okay guys, and I just realized that we have made a small mistake somewhere because we have only 23 months of data for each stock, and I had to go back through the code and actually figure out that on this step this part was missing, which was the data.log, selecting all the rows and then the dollar volume column. You can just rerun this cell and you can see that here our first month is in 2015 November, and after that it was 2020. So when you add the .log and selecting all the rows and the dollar volume column, you get the fixed data. Then we can rerun. As you can see up here, it's 2021, the first date. If we rerun it, it should be much backwards in the past. Yeah, so 2017, 31st of October. And we have to do that again for the factor data too. And if we run now, yeah, now we have 71 months, right? And the idea here is that we remove all the stocks that have less than 10 months of data. How do we do that? We can just assign that to observations, and then we can save valid stocks. That will be observations. That will be all the stocks that have more than 10 months of data. Observations, yeah. Those are our valid stocks, and now we can just use that as a filter. So factor data would be factor data, again factor data dot index dot get level values. We'll get the ticker values. Maybe I can show you what this is returning. This is returning yeah, an object with all the stocks we have in the ticker index part of our multi-index, and then we can just say is in the valid stocks, and this would filter out pretty much everything. We have to add this part. Okay. Okay, so I think, oh yeah, I missed this part. It should be valid stock index. Those are the stocks we are going to remove. So if we take that out, yes, so now as you can see, we had before we had 10,201 rows. Now we have 10,150. We've removed around 51 rows. And Yeah, with this step, we are now ready to calculate the rolling factor betas. We would like to do that simultaneously for all the stocks in our factor data. We can just use the same methodology with group by and apply a function that would be factor data dot group by, and then we're grouping by level 1 by ticker. Group keys should be false, and we can put that into brackets so we can continue on the next row. So apply lambda x, and now we want to use the rolling regression. Actually, we may want to explore the rolling regression, rolling OLS Python. It takes the ndog and xog. All right, we have to supply ndog and xog. So the ndog would be our return column, right? So x return 1 month, and our xog would be everything else. What we can do here is say x dot drop the return 1 month column, and this would return all the other, this would give all the other columns without the return. And actually we can add a constant here on the spot. So we add a constant, and I think the next one we have to supply the window. We decided the window to be 2 years, right? So that would be 24, right? 24 months. And there is another mean observation, the minimum number of observations required to estimate the model. We have to supply this one as well. This one is a little bit more tricky. We have to supply here to have at least the total number of columns plus 1. So that would be len x dot columns plus 1. And this should be our model. Now we have to say fit, and then params, and then we can drop the constant because it will return a constant as we added a constant up here, right? And I think this should pretty much work, except that maybe sometimes we would not have exactly 24 months of observations, but we still may want to run the regression. So what we can do is use as a window the value which is smaller than 2 values. So it either 24 months, or we can use the number of rows we have in the for the given stock, right? And we know that we have stocks with more than 10 months of data. So if one of the stocks have like 15 months of data, you just use the 15 months as a window instead of 24. And yeah, I think that should pretty much be it, right? Okay, series object doesn't have fit. Why? Maybe okay, so that's pretty much our rolling factor betas. We have calculated them. Now we can assign them to betas, and that's our rolling factor betas, guys. In the next step, what we want to do is to join them to our current features, and with that we'll have our full features dataset. But before we join them, we have to think about a little bit. Now we have the rolling factor betas where we used the factor at the beginning of the month and the return at the end of the month. So this beta we would actually know at the next month, right? At the end of the month, we'll be able to run the regressions and have the betas, but we'll have them in the next month. So we cannot just blindly join them to the features data we have so far. What we have to do is to shift them with 1 month forward before we join them to the data, because these values we would have not known in the same month. We would know the rolling factor beta, for example, for the end of October. We would know them in November. What we have to do is we have to shift with 1 month forward on the ticker level. So for each ticker, not like the whole data frame, if we just say betas dot shift, it will shift with 1 row downwards. And for example, the value of Verizon will come up here, right? Just see that. So Verizon is 0.3. If we apply shift, it's now here. So that's obviously not correct. So what we have to do is we have to first group by, and we can do that group by ticker, and then we can shift. That would now do it correctly. We can grab that and supply it here. And data will be equal to this. And the next step that we want is to impute the missing values of each factor with the average for that factor beta. How we can do that? We can say, first we can create a list with the factor columns. Factors would be just those 5 columns. We can say data.log all the rows, factors. We'll just select all the factors and all the rows. And then we can say the following: data.group by ticker. For each ticker, we'll select the factors again, and then we'll just apply a lambda function, lambda x, where we'll fill all the missing values with the mean of this factor. But I think because we are doing group by apply, we have to add the group keys to be false. And now we should have fixed our missing values issue. Voila. So now we don't have any missing values. So all the NAs are imputed by the average for this factor. And yeah, now we can just say drop NA if there are any. And we can say data.info to see our final result. And that is now beautiful, guys. This is our features data set. However, I see a column we don't need here, which is the adjusted close. We just have to drop it. Data is equal to data drop adjusted close, axis equal to 1. And this is our features data set, guys. So we have 18 features. At this moment, we are now ready to apply machine learning models. From here on, what we have to decide usually is for each new month, we have to form a portfolio with some of the stocks from our data set. So as we know, we have, for each month, we have the top 150 most liquid stocks. And now at the end of each month, we have to decide the stocks we want to have in our portfolio for the next month. That's where we can use a machine learning model. First, we can use a machine learning model to predict which stocks to include in the portfolio. As well, if we have a long short portfolio, we can predict which stocks to be long and which stocks to be short. But in this course, we are just focusing on long portfolios. So we can use a machine learning model to predict which stocks. As well, we can use a machine learning model to predict the magnitude of the position in each stock. So what is the weight in the portfolio? And the other way is to use a machine learning model, in our case, a non-supervised model, to decide which stocks to use in the portfolio based on grouping. That's why we are going to use a clustering algorithm, a K-means clustering, to keep things simple, because from this point on, things can get really complicated. But yeah, that so far was the preparation to get the data to fit into a machine learning model, guys. And yeah, I'm really excited. In the next step, we're going to fit a K-means clustering algorithm and split the data in a few clusters. Each stock will be assigned a cluster, and then we'll be able to analyze the clusters and decide what we do further. Let's move to this step. Okay, so in this step, we're going to fit the K-means clustering algorithm for each month and split the stocks into 4 different groups based on their features. Why 4? I've already did a little work beforehand, and I've estimated that the optimal number of clusters roughly on average for each month is around 4. So we'll use 4 clusters for each month from now on. The specifications about the K-means clustering algorithm is that it may assign the centroids of the clusters randomly, and then it assigns a given point to the cluster based on the distance from the centroid to that point. To help you understand a little bit more, so this is an example with the same data but different number of clusters specified when fitting the model. So in the first one we have 2 clusters, as you can see, really well defined, 3, 4 and 5. Whenever we initialize the model, we have to specify how many clusters we want the data to be grouped in, and the algorithm would go in, assign random points, and then the closest points to the centroid, so random centroids, the closest point to the centroid would be assigned to that cluster, and until that will be repeated until all points have an assigned cluster. How do we start here? Let's first import the K-means class from sklearn.cluster. We are going to import K-means, and now what we want to do, right, is fit a K-means model for each month and assign a cluster to each stock, so get the label. We can do that at once using the group by apply logic we've already used for the ATR and MACD. We can define a function that should be get clusters to take data or df, it's up to you. And then we'll create a new column called cluster, and here we'll fit the K-means model. So the K-means class takes first argument number of clusters, that would be 4, as we already know. I've done my research beforehand. And then we'll use the random state argument to be 0. This would ensure it works like random seed. This would ensure that we have the same results through different calls. And there is another really important argument here, the init. This is the initialization method of the centroids. Actually here for now we'll use a random initialization, but we can actually supply here the initial central points for the clusters, and we may use that in the future. So let's see the first result. We'll fit the model to the data frame, and then we'll get the labels. We will return the labels and we will assign them to the cluster column, and we'll just return the data frame in the end. And now we can say the following: data drop NA. We will ensure that we don't have any NAs in the data. Group by level 1 or date, and then group keys equals to false because we do group by apply, and then apply get clusters. This will take some time, but it will now go through each month and fit the K-means clustering algorithm with 4 clusters and assign the given cluster to each stock. Let's wait for this to run. Okay, so the clustering is finished. Let's take a look at the results. Now we have the cluster column, and in it we have the assigned values from 0 to 3. So 4 clusters, 0, 1, 2, 3 for each stock, and that is done every month. Now the next step would be to visualize actually our clustering job, which is pretty hard when we use more than 2 features, and in our case we have 18, but that's why we didn't apply normalization to the RSI, because now we can use it to visualize the clustering job in a better way. All right, so I've already wrote down a small function for that. Up here, this is a plot function. We just select the stocks for the first, the second, the third, and the fourth cluster, and then we just visualize them with a scatter plot. And my idea here is to do that for each month. So we can use this function. It will select, for the scattering, it will select the first column, which is the ATR, and the 7th column, which is the RSI. And let's do that now. put.style.use, we use the ggplot style always. And now for I in data.index get level values, and we'll get all the months. So unique to list. For each month, we're going to select pretty much this month, right? So data.xs, and then I level 0. So we're going to select the month, and we're going to use this function. So for each month we will just plot the clusters. However, we may want to add the month to the title, so we can do that in the following way. Date I. Let's run this thing and check our clustering job. All right, guys, so now for each month we have our clustering job. So those are all the stocks, and on the Y label we have the RSI values, and here we have the ATR values, and those are our clusters. As you can see, they're really well defined throughout the different months. And if you go through it, the first observation is that actually the clustering is working in such a way that all the stocks which are around 60 to 70 RSI are in one cluster. Then you have the two middles from 50 to 60 and from 50 to 40. And then you have the down cluster here around 35. And what we can see is that this assumption or this observation holds throughout each month of clustering. However, the problem is that, for example, in this month, cluster 0 is around 30-35 RSI. Cluster 1 is around 40 to 50, right? But then this is the same for the next month, but at some point, cluster 0 is around 50 and cluster 1 is around 60. Because the centroids are random, our clustering gets random. And my idea for the strategy we're going to apply is that we would like to follow stock's momentum. By stock's momentum, I would use the RSI as the main indicator, right? The stocks which are around 70 RSI are in an upward momentum. And I would like our strategy to invest every month in the stocks that have the highest upward momentum throughout the previous month. For that job, I would like to focus on the stocks that are clustered around RSI of 65 to 70, 75. But using the random initialization of the clusters would not work. And as we can see, so what we have to do now is to help a little bit the K-means clustering algorithm by supplying the initial centroids. But how we can do that? Let's check out the K-means documentation. Okay, so that's the init argument. So the default is K-means ++. We used random, but if an array is passed, it should be of shape, so this shape, and clusters and features, and gives the initial centers of the centroids. That's exactly what we want to do. And we want the initial centers to be based on our RSI indicator. Pretty much what we want is that all the stocks which are around 70 RSI to be for each month to be in the same cluster. Then 55 the same cluster, then 45 the same cluster, and 30 the same cluster. Obviously, that would be a little bit better than just deciding those thresholds ourselves. For example, if you want to select all the stocks above 70 every month, we'll have a different result than using this clustering algorithm to do the clustering around 70 for us, based on all the features we have in the dataset. Now we have to supply to the clustering algorithm this array in this shape with the initial centers. Okay, so let's do that. So first we would like to have the target RSI values, and that would be a list with the first target RSI value would be 30, 45, 55, and 70. Then our initial centroids would be numpy zeros, and we are going to use the target value. So the length of the target values, which is 4, and then the number of features, right? 4 and 18, because we know that we have 18 columns, right? 18 features, and that would be our initial centroids. However, let's run that. Yeah, I think I forgot that part. Yeah, so that's our array. However, up here we have to supply the centroids. What we are going to do is the following: all rows and this column, as we know that the seventh column, so the sixth index, the seventh column is our RSI column in the features data set. We're going to just change that to the target RSI values, and we'll get the following. Here we have the initial centroids, and that's our array we're going to use for the clustering job. We have to supply it here, but before that we would have to first drop the cluster column and rerun the whole clustering. So data is equal to data drop. This will now drop the cluster column and rerun the clustering and assign the centroids as we have supplied. This will ensure that throughout each month we'll have the same cluster label assigned to the stocks corresponding to the same cluster. As you can see, again, in the first month, in October, we have assigned cluster 2 to all stocks with RSI around 70. In the next month, it's cluster 1. We want that to be always cluster 2. That's why we are doing it. Okay, let's run it. We'll have to wait again for the model to fit. Okay, and it's done. We have fit now the model with our initial centroids, and we can just now rerun the visualization. Let's do that now. Okay, so now cluster 3 is assigned for stocks with RSI around 70, and this is consistent for each month. It's again cluster 3, cluster 3, cluster 3, cluster 3. And now we can use that down the road to select every month the stocks which are, for example, in cluster 3 to form our portfolio suite. And we know that cluster 3 is corresponding to stocks that have had a good momentum through the previous month. With that, we are ready to move to the next step, which is at the beginning of each new month, we are going to select the stocks we want to invest in for that month. Okay guys, so we're at the most exciting part. Now we are going to select stocks based on our clustering, and then we're going to form a portfolio using an efficient frontier optimized max Sharpie weights for those stocks. We want to choose a cluster based on our hypothesis, and as we talked earlier, my hypothesis here is that Stocks which had an RSI around 70 are having good momentum, and my idea is that this momentum should keep outperforming in the next month. And for this job, I've analyzed all the clusters throughout the months, and I saw that cluster 3 is always stocks around 70 RSI. And in this case, I would like to select those stocks for every month for my portfolio. How do I do that? We just select stocks corresponding to cluster 3 for each month. Okay, so here we can call that filtered data frame. And assign that. Okay, so now after we have our filter data frame, now the first step is to actually get, so at the end of October, right, on 31st of October, we had those stocks. That's our list of stocks which we would like to use to invest in November. My idea here is to create a dictionary with the first day of the next month and all the stocks for the next month in a list. To do that, we'll have to do the following. So filter df, we first reset the index. We reset actually only the first level. Okay. All right, so we've done that. And now we can do the following. We can just use the index and add one day to it. So pandas date offset 1, which would move each index with 1 day in the future. As we know, all the indexes are the last day of the month, so we'll have the beginning of the next month like this. And the next step would be to do the following. So we can reset the index, and then we can set the index again to be a multi-index. So we'll have date and ticker. Let's see. All right, perfect. If that doesn't work to you, you can do unstack and then stack, but it's not necessary at the moment. We do this step, and then the next step would be to create the dates object. So dates would be index.get level values. We'll get all the months. And then what we have to do is to create this dictionary, which is having as key the date, so the beginning of the new month, and value would be a list of all the stocks for that month. We can call that fixed dates. It would be a dictionary. And then for D in dates, we do the following: fixed dates dot D. Here we'll fix it to be string f time in our format, year, month, day. And this would be equal to filtered data frame. Pretty much we will select each month, right? We'll select each month. And then we get the index. After we select the month, the index will be the tickers. And then we call it to list. And that's pretty much it. This should give us, this should create for us this dictionary. And voila, we have it. So now we have the first day of the next month, right? And the stocks list, the stocks we want to invest for the next month into a list. And actually we can now really easily use that to create our portfolios. And with that, we are ready for this step. So the next step is to define the portfolio optimization function, we're going to use the portfolio opt package and the efficient frontier to have a portfolio which maximizes the Sharpe ratio. So, okay, let's move to define the portfolio optimization function we'll use. To do that, first we will import from portfolio opt package a few different classes. So from pf opt dot efficient frontier, we'll import the efficient frontier class. And then from pf opt, we'll import risk models. And again, from pf opt, we will import the expected returns object. Okay, so now what do we want to do? So at the beginning of each month, we have the list of stocks we are going to invest, and those stocks we have to assign weights to them. We have to find those weights. We are going to use this package to optimize and find those weights for every month. We'll define this optimize weights function, which will take two arguments. Prices, actually one argument for now, and we'll add another one in the later on. So first the function will take only the prices of all the stocks we want the weights to be optimized for. First, we'll have to calculate the returns of those stocks. So we will use the expected returns. From expected returns, we use a method called mean historical return, which take an argument prices, and we will supply the prices as well. It takes an argument frequency, and that would be 252 days, so 1 year of trading data. Then we have to calculate the covariance, and this time we'll use the risk models. So from risk models, sample covariance, again we have to supply the prices and the frequency, again 1 year of data. After we have calculated the returns and the covariance, we can now initialize our efficient frontier object, efficient frontier, and now we can take a look by portfolio opt efficient frontier. Let's read the docs. Okay, but that's the general. We want the mean variance optimization. Okay, so the efficient frontier takes the following arguments. So expected returns, the covariance matrix, weight bounds, and then the solver. All right, the expected returns, maybe we can just copy those. The expected returns will be our just calculated returns. The covariance matrix would be cov, and we will keep these weight bounds for now. I will show you why. And we'll use the SCS solver. And after we have that, we can just calculate the weights. Weights will be from efficient frontier. We'll use the max Sharpe method. That should give us the weights. And then in the end, we can get the clean weights, which will be round the weights and clips near zeros. So we want the clean weights. We'll just return ef.clean weights. And that is our portfolio optimization function. So obviously we have to supply the 1 year prices to this function, and it will calculate the returns of those stocks. So we have a date frame with 1 year prices of all the stocks for a given month. This function will calculate the returns, it will calculate the covariance, then it will feed the efficient frontier optimization and come up with the optimized max Sharpe ratio weights and return the weights. However, there is a small specification, and that is the weight bounds. Pretty much this is the bounds for a single stock, what can be the constraint for weight of a given stock. At the moment, it is from 0 to 1. So after the optimization, we may have some stocks with 0 weight, and we may have a single stock with 100% weight. Obviously, we don't want that, so we will come back and fix it. But yeah, that's pretty much our function. For diversification purposes, we would like to actually have a maximum weight of 10% of our portfolio in a single stock, so we can already assign that to be 0.1. But for the lower bound, we may use a more dynamic metric, so we'll create an argument here, lower bound, which would be equal to 0. But for example, for the lower bound, when we do the optimization, we may use half the weight of an equally weighted portfolio. For example, for a given month, we have 20 stocks. An equally weighted portfolio would have 5% in each stock. So we may assign half of that weight. Let's say with 20 stocks, we may have the smallest weight to be 2.5%, half of equal weight, and the maximum to be 10%. And with this, we will ensure that we have a diversified and well-balanced portfolio. And yeah, guys, with that, we're ready for the next step. And in the next step, we're going to download fresh daily prices of all the stocks that may end up in our portfolios. As we know, the first portfolio we are going to form at 1st of November 2017. And from our optimized weights function, we know that we need at least 1 year of data prior to the optimization. So the starting date of our of the download should be 2016, 1st of November at least. And to download the prices, we can just use Y-Finance package. The first step would be to create the stocks list. Actually, we can go back and use the data object. That will be the 150 most liquid stocks, because any one of them may end up in our portfolio. We want the data for them. So data.index.get level values. Get level values. That will be ticker, right? Or ticker values, unique. And then to list. So we have the stocks list. And then we can create the new data frame. The new data frame will download from Y-Finance. Tickers will be our stocks. And now the start date. Yeah, as we know, the first date we want at least 1 year before that. So we can actually, to make things dynamic, we can use the data.index get level values, but here we will get the months. Then we take the first value, so the first month, that would be October 2017, but we can just say minus pandas date offset, and then months equal to 1, so minus 1 month. This would return us exactly end of September 2016 actually. I went to 2017. Okay, so we want 12 months. We want 1 whole year. I'm sorry, my bad, guys. That's exactly what we want. So that would be our start date, and our end date would be pretty much the same. However, that would be the final value from our unique month index of the date object. And that's pretty much it. This will download the data we need for our optimization. And after this is downloaded, we are ready for the next step, where the most interesting part is coming. We're going to loop over the fixed dates dictionary, and for each new month, we're going to get the stocks, optimize the weights, calculate the daily portfolio return, and then calculate the whole time period portfolio return by rebalancing and optimizing every new month. The download is done, and we're ready to move to the next step. First, we're going to calculate the returns, the daily returns for each stock from the fresh new data we just downloaded. And then again, we're going to loop over each month, select the stocks for the month, calculate the weights, form the portfolio, and calculate the daily return for our portfolio and for our strategy. All right, so let's start. First, you want to create the returns data frame. It would be, we calculate log returns. So from new data frame, we select the adjusted close column, take a log, and then the difference. That will give us the returns data frame. Awesome. After we have the returns, we'll create portfolio df, which would be an empty data frame. And then we will loop over. So for start date in fixed dates.keys, so we're going to loop over our dictionaries. For start date, so for each date, we are going to first get the end date. So the end date should be the end of the month, right? We're investing for 1 month and then we're rebalancing. So at the beginning of November 2017, we want to select the returns from this return data frame. We want to select the returns for the next month, right? So the end date would be the end of November 2017. That will be pandas to date time start date plus pandas date offsets. Actually, I think here we'll use offsets, and then month end. And we can call the string ftime method. So we have the right format. We can print that. No, actually we can print both the start date and we can print the end date. For each month we have the start of the month and the end of the month. And now the next step is to get the columns for the month. To do that, we can just say the following. So columns would be equal to fixed dates, and we are just going to select the start date. And those are going to be our columns, right? So those are going to be the stocks for each month that we are going to form portfolios with. After we have the start date, end date, and the stocks for the given month, now we want to calculate the weights. But to calculate the weights, we need to do the optimization. And as we already know, to find the optimized weights, we need a 1 year data prior to the start date. And it has to be daily. So for that data, we'll use the new data frame that we've just downloaded, which contains the prices. And pretty much what do we want? So to calculate the weights for all stocks at the beginning of November 2017, so for all those stocks, we would have to input the prices for 1 year prior of those stocks into this function, which will calculate the weights, and then we'll have the weights for the first month, so for the November 2017. In this case, we would have to create an optimization data frame. First, we have an optimization start date, and it would be pandas to date time start date. It would be the given start date, 1st of November 2017, minus pandas date offset, and we will supply months minus 12 months, exactly. So exactly 12 months ago would be the optimization start date, and we will create an optimization end date as well. So the end date would be actually, again, the start date minus however 1 day. And now we can print to visualize everything we have so far. So we have the start date, we have the start date, then we have the end date, then we have the stocks that would be included in a given month, then we have the optimization start date and optimization end date. date of set. My bad. So date of set. And now for this month, so for 2017, from 1st of November until the 30th of November, that will be the stocks in our portfolio. And we'll have an optimization. So to calculate the weights for those stocks, we'll have an optimization date frame, which will be for exactly 1 year prior to the starting date. So from 1st of November 2016 up to 31st of October 2017. And now the next step is to calculate the weights. For the weights, we are going to use, that was my point one. So we're going to use our optimize weights function. And here we have to supply the prices of the optimized weight and the lower bound, right? The prices would be actually an optimization data frame. This optimization data frame, we can use the new data frame, which contains prices, right? And we can select the following dates from the optimization start date to the optimization end date. Then we'll select the adjusted close, and we want only the columns that we're going to use for the portfolio for this month. And that will be pretty much our optimization data frame. So in this case, yeah, when I run it, so that's that, because in the for loop, the last values for the start and the end date would be the last values based on the last value of the fixed date key. So it's filtered out from 3rd of October 2022 up to 29th of September 2023. That's around almost 1 year. But what we are going to do, for the sake of simplicity, because our first start date is 2017, 1st of November, we are going to select the following date: 2016, 1st of November until 2017, 30th of October. And this is going to be our optimization data frame to calculate the weights. We are going to supply that up here. As well, we have to supply the lower bound, that for each stock, what will be the lower bound? The upper bound, we know it's 10%. Maybe we want to make it this one dynamic as well, but for now, let's keep it 10%. But the lower bound, we want to be half of an equally weighted portfolio. So an equally weighted portfolio is going to have weights which are pretty much equal to 1 divided by the number of assets in the portfolio, so the number of columns. In this case, we would have 10 columns, so 10 assets for a given month. So the equally weighted portfolio would have 10% for each stock. Half of that would be the number of stocks multiplied by 2. I mean, 1 divided by the number of stocks multiplied by 2, and that will be 0.05. And now we can wrap that around in a round function. So we are always sure we have a round weight. And now we can run it to optimize our weights. However, I think that up here, our columns are actually not the right columns, because we would have to select the first optimization date. So that would be 11. This is the list of our columns. And our optimization data frame will be the following. And now we can input it here and check out the weights. This now looks quite interesting. First, let's take a look at the lower bound. So the lower bound is 0.01. If we apply, it will be 0.012. Okay, maybe we can use a rounding of 3 instead of 2. Okay, now this looks better. Those will be the weights of our portfolio in November 2017. As you can see, first stocks, they have a weight of 0.01, so 1.2% of our total portfolio. And then we have this stock, which has 10% of our portfolio. This one has 7, this one has 6.8%, 5.9, 3%, 4%, 4%. That's what we are going to do at the beginning of each month. We are going to optimize and find the weights for our stocks for that month. Okay, now we can implement that into our optimization. So up here, we are going to provide the weights. And next step would be to create the returns date frame. But actually before that, I think we can turn that into a date frame. So we can say the following: weights equals to pandas data frame, and then weights and index is panda series. And now we have the weights as a data frame, and we can now potentially use that with the returns data frame to multiply the weight of each stock for the given month by the return for that stock for every day. And this way we'll be able to calculate the portfolio return for each day. Okay, next step would be to create a temporary data frame, which would be equal to returns data frame. And here we'll use the start date up to the end date. We are going to filter the beginning of month, so that would be 2017 first until 2017 30th. That will be our temporary date frame. Let's see what we have here. So we pretty much selected the stocks and the returns of the stocks for the given month, the selected stocks. And now what we would like to do is just merge with the weights data frame to get the stock return for each day and the weight for that day. We can do the following. First, stack. We are going to stack, and then we're going to say to frame return. Now we have for each day all the stocks and then the return column. And now we want to reset the index. We are going to reset the date index. And next step is to merge with the weights. I'm looking something like that. We can say stack to frame weight, and we can remove, we have now a multi-index up here, so level 0, level 1, so we want to remove the 0. We can say reset index level 0, drop equals to true, because we want to just drop it directly. And we are going to merge those two, left by the index, so left index true, right index true as well. And we'll get something which looks like that. The next step would be to reset the index and set a new multi-index date, and I think this one doesn't have a name right now, so it would be just called index. And now we have almost what we want, so we can say unstack and then stack. And now we have the data frame with the return for the given date and the weight of the stock for the whole month of our stock. And we can call this our temp date frame. The temp date frame was initially the start date to the end date. We can grab that, put it up over here, and now we can grab this part as well to put it over here. And let's take a look again. Now we can just simply use a vectorized operation. We can multiply the return column by the weight column, and then we can get the weighted return for each stock for every day of the given month. And let's do that. But before, maybe we would like to fix the index. So the index to be the index names actually. So date and ticker to keep things tidy. Names. And now we would like to calculate the weighted return for each stock, which would be just the return column multiplied by the weight column. And now we have the weighted return for each day, for each stock. And the next step would be just to calculate the sum of the daily weighted return, which would be our portfolio return for the given day. And we can do that by saying the following: group by level 1 or date, level 0 or date, whatever you prefer. So weighted return dot sum. That will be the portfolio return for every day, and then we can just say to frame and call it strategy return. And that will be our strategy return for the selected month. Obviously, we are looping over each month, and we are doing the operations for every month. We can assign that to the temp df and move it over here. And the next operation would be just to, concat this to the portfolio date frame. So portfolio date frame would be equal to pandas concat portfolio date frame with temporary date frame axis equal to 0, or the default axis. And that should be it, guys. So we have we loop over each month. We select the optimization date frame. We are doing the optimization, calculating the weights. Then we are merging the weights with the returns of those stocks for the given month. And we're calculating the weighted return for each day for our portfolio, which is our strategy return for every day. Let's run that and see if it's going to work out. Okay, so we have an error, which is return. Okay, so I found how to overcome the error. We'll just implement a try and except clause. So try, and we'll try to run that, except exception SE, and we'll just print the exception. As well, I was digging through the code and I figured out, guys, that we have forgot a really important part of it. And up here, we don't specify the optimization data frame. We would have to add that. The optimization data frame was pretty much our new data frame, where we select the optimization start date and the optimization end date. And then we select the adjusted close and the columns for the given month. And with that, I think now the optimization part should be pretty much fixed. And we have something. So please check your objective constraint or use different solver. Solver status infeasible. Okay, yeah. So this is actually happening from time to time, and pretty much the solver is not able to optimize the max Sharpie ratio weights, and instead it's failing. If we visualize the portfolio returns, you can see those periods where there is no data. So pretty much the solver has not optimized the portfolio. We didn't have any weights and we end up with no investment for those months. A workaround would be actually to do the following. I've really spent some time on that part, and unfortunately there is no easy solution for this optimization failing for the max Sharpie ratio. The only workaround I figure out is to implement the following. Whenever the optimization fails and we don't have the max Sharpie ratio weights, we will use equal weights for our portfolio. As simple as that. We'll do the following. So we'll try to calculate the weights, and then if this doesn't work out, we'll do except, and then we'll print that max Sharpie optimization failed for start date. Continuing with equal weights. And let's see if this is the issue. If we run that now, it should print, yeah, exactly. So for those months, the max Sharpie ratio optimization failed, and we have to continue with equal weights. So how do we do that? We'll do that the following way. We'll create a new variable, which is success, and it will be equal to false. However, if the weights have been optimized, it will be equal to true. All right, and then we can just do the following. So if success is false, our weights would be pretty much, we would create a pandas data frame with our weights. So pandas data frame, but let me take this out of here. Let's put it down here. We'll create a pandas data frame, and then we want equal weights. So we can just use this part right here. We want equal weights. So that will be the equal weight, right? One weight, but we want it for the number of stocks in our portfolio. So it will be for I in range len optimization df.columns. Yeah, that would be our equal weights. And then we have to supply the index, and the index would be just the columns as a list. So columns to list, and the columns would be a pandas series 0, and this would give us a data frame containing the stocks for a given month with their weight assigned as an equal weight, and we can just transpose that and have it like that. So this would be our equal weights data frame if our optimization fails, and we'll have only equal weights whenever the optimization fails. And after implementing that, so yeah, pretty much you can implement a print statements throughout the code to double check if we work correctly, but I can assure you that it's working correctly. And now if you want to visualize the returns, just do a simple plot. You see that we have the returns throughout the whole time frame. And with that, pretty much, guys, we are ready with our strategy portfolio building. We may want to apply to drop duplicates up here if we have any duplicates. I think we don't, but just in case. And yeah, with that, guys, we are ready for the next step. And in the next step, we're going to visualize the returns of our portfolio and compare it to a benchmark, which in this case would be the S&P 500 index itself. It will be really interesting to see the results of all that hard work so far. So let's move to that part. And to compare our portfolio to the S&P 500, first thing would be to just download the returns for S&P 500, so we can say so SPY, and we have we would download the from Y Finance tickers. Our ticker would be SPY, the ETF on S&P 500. The start date, we can just supply like 2015, 1st of January. And the end date, we can supply daytime date today. And now we would pretty much create a new object. Let's call it spy_ret, so spy return. And here we'll just take the log return of spy, just close, then difference, then drop an A, rename, and yeah, first let's check spy_ret before we rename. Okay, so this is the log return of spy for each day, and now I'd just like to rename the adjusted close to benchmark return or spy buy and hold. It would be adjusted close to spy buy and hold, axis equal to 1, and then we can use the portfolio date frame to merge the spy return to the portfolio date frame. So left index would be true, right index would be true. By default it's an inner join, so we don't have to worry about okay, so we'll just we'll just rerun this cell, and then we'll rerun this one. And now we have the strategy return and the spy buy and hold return for the same dates. And we can move to the next step where we would like to, calculate the cumulative return for both the S&P 500 and for our strategy, and plot them to compare them in time. We'll do the following: matplotlib_style.use ggplot. I think we've done that previously, but just in case. And now we want to calculate the portfolio cumulative return, and that would be from NumPy expanding window. So NumPy xp log from portfolio data frame, and then after that we'll call the cumsum, and this should calculate the cumulative sum, so starting from 1, but we have to say -1. And now we would have the cumulative return for our strategy and the S&P 500 itself. Now what we may want to do is just to select, for example, that we want the portfolio return up to a given point. Let's say we want it up to 29th of September, so we'll just say up to 0.920 29th, and then we can plot that. We can say fixed size 16 by 6, and that's pretty much that's our comparison, guys. We can add a title, so plt.title, unsupervised learning trading strategy returns over time. As well, we may want to pty label return, and maybe we would like to fix a little bit the axis up here to be in percentages, so we can call this the following: gca dot y-axis set major formatter, and here we can supply a formatter. Like there is a formatter from mtick, but I think we have to %formatter. I think we have to import it up here, so we have to import from matplotlib ticker as mtick. Import map as mtick, and this would do it. Y-axis set major formatter, And that is pretty much our strategy, guys. Up here we have selected the 150 most liquid stocks for each month. We have calculated 18 different features on each stock. Then we used a k-means clustering algorithm to assign a cluster for every stock. We supplied our custom centroid, we initialized our centroids with a custom array. And then for each month, we've optimized the portfolio to have the maximum Sharpie portfolio weights for every new month, and form this strategy using S&P 500 stocks. And now we compare to the return of the S&P 500. Nevertheless, this is not a financial advice. You shouldn't use that anyway. If you come up here and just change the logic for selecting the stocks from third cluster to zero to cluster 0, everything will be changed on the spot, and you see that the results would change dramatically as well. That's just example of how we can implement machine learning into trading strategies and forming portfolios, etc. So that's pretty much it for this strategy, and into the next one we're going to form portfolios using Twitter sentiment data. I'm looking forward to that, and let's move to the second project. In the second project, we are going to build a Twitter sentiment investing strategy. For this project, we are going to load a data set which will be available for you to download from the description of the video. There is a link where you can download the dataset used in this project and in the third project. As well, the notebook for all three projects would be available on that link too. So we will be loading this dataset containing Twitter sentiment data on stocks from Nasdaq 100. This strategy would be focused on Nasdaq 100 stocks, and we're using Twitter sentiment data. The idea here is that I would like to, it will be a smaller project than the first one, but I would like to show you how we can create a derivative feature from the Twitter sentiment data to create potential value for our investments. First, we'll start by importing the packages. Those are the packages we're going to use: Pandas, NumPy, Matplotlib, Datetime, Y-Finance, and the operational system package. We'll import datetime as DT. That's the only thing we're going to change. And again, we're going to use ggplot as our Matplotlib style. First, let's define our data folder. So this would be the path to the sentiment data file you're going to download. So it would be a CSV file. This is my folder which contains the data, and you'd have to assign the path to your folder up here. Let's load the data. So sentiment data frame would be pandas read CSV, and here we have to supply the path os.path.join data folder and the file name. So the file name is sentiment data.csv, and let's run that and see what we have here. That is the sentiment data we have. We got the date, the symbol, and the corresponding Twitter posts, Twitter comments, Twitter likes, Twitter impressions, and the Twitter sentiment. The Twitter sentiment is calculated by the methodology used by the data provider. We just use it as it is. Here, the first thing we want to fix is the date. We want the date column to be date time, so pandas to date time. And next step is to set the indexes. Again, we're going to work with the multi-index in two levels. So sentiment data frame set index. This is going to be the date and the symbol. Date and symbol. So far, so good. Now I would like to calculate a quant feature out of this data, and it would be called, actually I'm interested in the engage, the Twitter engage each stock has. Not only just the raw sentiment or the raw impressions, likes and comments, but I'm interested in the engagement that people have on the posts on Twitter for this company, because we know that there are a lot of bots on Twitter and they are messing up the data, skewing the data on some posts or some symbols. And actually I would like to have engagement ratio which may be more informative than having just the likes or the comments or the sentiment on its own. And this engagement ratio will be pretty much the Twitter comments divided by the Twitter likes. If a given company has a lot of likes but no comments, we know that this is bots activity. But if there are a lot of comments and a lot of likes as well, and actually the comments are as much as the likes or even more, we know that people are engaged on this stock. Let's calculate the engagement ratio. Engagement ratio. And this engagement ratio will be pretty much Twitter comments divided by Twitter likes. So how much are the comments compared to the likes? And that's our engagement ratio. We have this engagement ratio for each stock for every day. And now we may just want to filter out the data frame to contain only stocks that have, for example, more than a given amount of likes. So let's say we want stocks that have more than 20 likes for a given day and more than 10 comments on a given day, because otherwise it's just random noise. So Twitter likes, we would like to have more than 20 likes, and we would like a stock to have more than 10 columns to be kept into our investment universe. And with that, we are pretty much ready with the first step. We're following pretty much the similar logic to the previous project. However, here we're going to create an equally weighted portfolio. We are not going to implement the efficient frontier optimization. Every month we would decide an investment universe of top 5 stocks and just invest into them. And now, after we have calculated the engagement ratio, now we want to pretty much calculate the average engagement ratio for each stock for every month. And we can do that the following way. So we will reset the symbol index, the symbol part of the index. We'll reset symbol, and then we'll group by. We'll group by for every month and every stock. We'll group by on the monthly level and the symbol level. And then we're going to, maybe we can put that into brackets. Then we're going to select the engagement ratio column and calculate the average engagement ratio for the whole month, pretty much. And now we can assign that to a new variable, new data frame called aggregated df. And now we can calculate the cross-sectionally the rank for each month of all the stocks based on this engagement ratio. How do we do that? We say a new column rank. We are going to group by level 0 or date. So we are grouping by each month because already we have aggregated to the monthly level, right? So we group on each month, and then we select the engagement ratio, and then we are doing the following. So on the next row, we're going to say transform lambda, but maybe we can put that into brackets and move that on the next row. So lambda x, and here we'll just say x.rank ascending equals to false. And this would create a new column called rank cross-sectionally for each month based on the engagement ratio, and the stocks with the highest engagement ratio would have the highest rank. And we can obviously see that already. So now we want to pretty much select for each month the top 5 stocks for each month based on this rank and grab them to use similarly to what we did in the previous project. Grab the start date and the stocks that we want to include in the next month, and then calculate the returns, but this time in an equally weighted fashion. So let's do that. I'll cut those cells and Yeah, now we'll just select the top 5 stocks for each month. So we'll do the following. Aggregated date frame, rank where is below 6. And now we have the stocks with the highest engagement ratio for each month. We can assign that to filtered DF date frame. And after we have the filtered DF date frame, we can just reset the symbols part of the index. So reset index level equals to 1. And then we'll just fix the index again the same way we did last time. So we'll just add 1 day to the index. So plus daytime pandas date of set 1 day. Let's see what this would give us. Now we have the beginning of the next month and the stocks we want to invest in for the next month. So those 5 stocks for each month. And yeah, pretty much next step is to reset the index and set again the multi-index. We'll set the multi-index again, date, symbol, and visualize the top 20 rows. So far so good. Now for the beginning of each new month, we have the top 5 stocks by engagement ratio. And now we would like to create the fixed dates object like we did in the first project. From dates would be equal to filter date frame, index, get level values, date, and here, yeah, unique and to list. So we make a list. And fixed dates would be again a dictionary, empty dictionary for the dates. Pretty much we are following the exact same logic we did in the previous project, so it's quite straightforward. I hope this time for you guys. However, yeah, in this project we are not doing the efficient frontier optimization, just rather use a weekly weighted portfolio. The idea here is to show you how we can extract value from different data sets. And yeah, as you can see now, for each new month we have the list of 5 stocks we are going to invest in. And the next step would be to download the fresh prices. To do that, we can first create our stocks list. It would be equal to sentiment data frame dot index get level values symbol, and again dot unique to list. This is our stock list, and we can create a new date frame prices DF where we are going to download again from Yahoo Finance. Our start date we can use, as you can see, we can use just the 1st of January 2021 to be sure we have enough prices. And the end date would be 2023 1st of March. So 2023 1st of March. Awesome. After we have our list of stocks for each month and the prices, we can move to the next step where we are going to calculate the portfolio returns following similar logic to what we did in the last section. So from prices DF, we can select the adjusted close column and calculate the log returns for each stock. And yeah, pretty much call that returns date frame. So after, and we can drop the NA values in the end. After we have the returns, we can now create portfolio date frame, which is just an empty date frame. And for start date, in fixed dates dot keys, print start date, just to visualize what we have so far. So for each month we have the start date, and now we want the end date for our portfolio. So end date would be pandas to date time, start date plus pandas offsets dot month end, which would give us the which should give us actually which should give us the end date of the same month. Okay, pretty much we have that. However, we would have to add the string ftime method in the end. Like that. That's pretty awesome. So what was the next step? The next step was to select the columns for the given month. That would be the stocks we are going to invest for that month. And these will be fixed dates, start date. So for each month, the stocks we have to invest for that month. And now we can create our temp date frame, where we would be calculating the equally weighted return for our portfolio for every day. This would be returns date frame. Here we'll say from start date to the end date. And then for the selected columns, we're going to calculate the mean, the average by columns. So the average daily return, and we call that in the end, we say to frame, and then portfolio return. Portfolio return. Next step would be just for each month to concat this portfolio return. And with that, we have calculated the equally weighted portfolio return for every month for those stocks we have selected using our methodology about aggregated monthly average engagement ratio for every stock, and then ranked cross-sectionally. And now we are ready to pretty much visualize the return, the cumulative return of our portfolio, and compare it, for example, to a benchmark like NASDAQ, right? Those stocks are constituents of NASDAQ, so we may want to compare it to the NASDAQ index as a benchmark. Again, guys, I've said it in the beginning of the tutorial and the course, we're using stock lists which are not survivorship bias free, and that is really important and most probably skewing the results upwards. So you should always use survivorship bias free stock lists when you're researching strategies. So now what do we want? We want to just download the prices for the NASDAQ or the NASDAQ ETF, which is QQQ. So we would use start date to be 2021, 1st of January, and the end date would be pretty much the same as for our portfolio, so 1st of March. And now we can calculate the NASDAQ return, so QQQ return, that would be log from the adjusted close difference, and we may want to rename it to NASDAQ return. And with that, we're ready to merge together the QQQ return to our portfolio date frame. So we merge by index. By default, the merge is always using inner join, so we are not obliged to specify that. Or maybe we are. No, we are not. And Now we have the portfolio return for every day and the Nasdaq return for every day. And the next step would be to just visualize. So we can say the following: portfolios cumulative return will be equal to, we'll calculate that in a NumPy expanding window where we take a log from the return of both portfolios, and then we apply the cumulative sum over the whole expanding window. So for each new addition, we run the cumulative sum. In the end, we have to subtract one, and that's pretty much ready for plotting. So we create a plot with a fixed size equal to 16 and 6, and we can set a title like Twitter engagement ratio strategy return over time. As well, BAT GCA y-axis, set major formatter. That would set the y-axis to be a percentage. So we'll use the percent formatter. As well, we'll give a name to the y label. And we just run beauty show. And that's pretty much our second project, guys, about the Twitter sentiment investing strategy with monthly rebalancing of an equally weighted portfolio. Our stock selection criteria is based on the engagement ratio, which we calculate as the Twitter comments divided by the Twitter likes for each stock, and we select the top stocks which have the highest average engagement ratio for every month. If you want to change the selection criteria, for example, if you want to select the stocks which have on average the most likes for every month, we can just simply do that. So copy this column, put it up here, then put it up here, and now we have pretty much the ranking done by average Twitter likes throughout the month. And if we run the symbols down, or the cells down below, it will be redone using the likes. And yeah, as you can see, when we use the likes, our strategy underperforms. However, if you use the comments, maybe we can try with the comments to see what would be the results with the comments. Similar results, however, a little bit higher outperformance. So the idea here is to show you that if we have alternative data, we may need to implement some calculations to get derivative features, which then may be valuable for our research and for our strategies. That is the main idea here. And if we return the engagement ratio, we run the whole thing, we are able to see the difference in the results. Obviously, the engagement ratio, by using the engagement ratio, we've created a little bit of value above the Nasdaq itself. And that is pretty much it about the second project. And we are able to now move to the third project, where we are going to create intraday trading strategy on a simulated one asset data using a GARC model, so a model to predict the 1 day ahead volatility. And it will be a really interesting one. So I'm really excited to move to the third project, and let's get into it. In the third project, we are creating an intraday strategy using GARC model. We are going to use simulated daily data and simulated intraday 5-minute data on a single asset, and we are going to create two signals on two different time frames, on the daily level and on the intraday level. So on the daily level, our signal would be driven by the GARC model volatility prediction, We are going to fit in a rolling window for every day a GARC model and predict the volatility for the next day. And from that, we're going to calculate the prediction premium and derive our daily signal out of that. On the intraday level, we are going to calculate technical indicators and create a signal following intraday price action pattern and merge with the daily signal and calculate our final signal intraday only for those days where simultaneously we have the intraday and the daily signal. And whenever we have the intraday signal, we are going either into a long or into a short position, and we're holding until the end of the day. And that's pretty much the strategy, guys. Let's start by first loading the data we're going to use. So the data, again, it will be available for you to download from the link down in the video description. First, we start by importing all the packages we'll be using for this project. They are matplotlib, arc. We'll use the arc project for the GARC model, then pandas, numpy, and the operation system package. Again, our data folder, you have to provide the path to your data folder, and we can start by loading the data. So daily data frame would be pandas read CSV, allspath join, and then the daily data frame, which is simulated daily data.csv, and this would be our daily data. Here we would have to fix the date. We use pandas to datetime, and we supply the date as well. Then we are going to set the index to the daily date frame to be the date. Pretty much standard stuff. And I have already calculated the log return, but to repeat that, I'll just calculate the log return, which would be numpy log from the adjusted close, and then we just do the dot difference method. And so far so good. That's our daily data, and our intraday data would be intraday 5-minute DF. Again, we're going to load it using pandas read CSV, so path.join, and the name of the file is simulated 5 minutes data.csv. We can comment out this code, this one as well. And here, first step, we need to fix the datetime column to be datetime. So pandas to datetime, that's the first step. Then we want to assign it as an index. And the next step would be to calculate this date column. So we can just redo that real quick, or we just cast it to data. We already have it, so we'll cast it to datetime. But if you're wondering what it is, it's just selecting the index and then date, which would give us the date column. And with that, we're pretty much ready with loading our daily and intraday 5-minute data, and we're ready to move to the second step. So in this step, we're going to define a function which would fit a GARC model and predict the volatility for 1 day ahead in a rolling window. We'll use a 6 months rolling window for that. But the specification here is that whenever you fit a GARC model, you need to supply the autoregressive and moving average orders. You need to actually find those orders. And to do that, I've used a brute force approach where I fit 16 models with a combination for the autoregressive and moving average orders from 1 to 4 and combinations between them. So I fit 16 models. Then I've extracted the mean square error and the Bayesian information criterion, and pretty much I chose the best model to be the one who is minimizing the Bayesian information criterion. So I found that the best GARC model on this data is having autoregressive order of 1 and moving average order of 3. So P equals to 1 and Q equals to 3. So that's a really important clarification. First, you start by calculating on the daily date frame the variance, or actually the rolling 6 months variance of the log return. That would be the variance. And we may want to visualize that. This is the variance of our data, the variance of the log return of our data through time. And now we would actually want to, for the sake of simplicity, I'll just filter out the data to be from 2020 onwards. And now I'm going to create a predict volatility function. So we are going to predict the volatility for every day. So far we have the variance. Pretty much the volatility is predicting the variance with a GARC model. When you fit a GARC model, you can predict the variance or the mean of the series. We're going to predict the variance of our asset for every day, and we would have to do that in a rolling window. So first we create the best model, which would be where you're going to use the ARC model, and here we have to supply y, which will be our x or the series, then p is the order, the autoregressive order, the moving average order, q. So those values we have to find with the brute force approach, as I did. I mean, fitting 16 or 25 models, collecting the metrics, the mean squared error, the Bayesian information criterion after you have run the model, and choosing the one which is minimizing the, for example, the Bayesian information criterion. That's the best model. So after we have supplied arguments to the ARC model, next we are going to fit the model. Here we would say the update frequency to be every 5 steps and this position to be off. And this is our best model. And now we can forecast, right? Variance forecast. So from the best model, we are going to forecast horizon equals to 1. So for 1 day ahead, our data is daily. So for 1 day ahead. And then after the forecast is done for next day, we have 2 columns or 2 values, the mean or the variance. So we choose the variance and we are going to choose the last value. So last row of the first column, we may want to print the date. So x.index, last date, the one we are going to forecast for. Then we'll just return the variance forecast. And this is our prediction function, guys. Now we'll just say the following: predictions, and our predictions are going to be based on the log return. We're going to apply a function in a rolling window of 180 days, the same way as we did for the variance, 180 days. And here we say lambda x is equal to predict volatility x. And we can now pretty much run that. Okay, yeah, my bad. There is no dot up here. Where is the problem? Okay, I think, yeah, it's iLock here, and this will now just run in a rolling window, fit the best GARC model. We know that the best GARC model for our data is autoregressive order of 1, moving average order of 3, and yeah, we just have to wait for this thing to run and predict the volatility for the whole data set. After we are done with that, we will move to the next step, where we are going to calculate the prediction premium and form a daily signal out of it. Okay, so the model is done fitting and predicting the variance, and we can now take a look. We have the variance and the predictions. Actually, if you look closer, then the values are pretty close and similar. Actually, we may want to visualize them if you're interested, guys. Let's see what we have here. So we have the variance and the predictions, and yeah, maybe we can just plot them. So the variance is more stable than the predictions, and as you can see, the predictions are exploding here or there, but we may deal with that if we apply a rolling average or a comma filter model on the predictions. They will smooth them out considerably. However, for the sake of this strategy and this course, I'm not going to implement that, but usually you may think about it, you know, like signal reduction techniques. Okay, so the next step, we are going to calculate feature called prediction premium. And after we have the prediction premium, we'll calculate the 6 months rolling standard deviation of that prediction premium. And from there, we'll be able to calculate and create our daily signal. The prediction premium would be a very simple formula. It would be equal to predictions minus. So from the predictions, we're going to subtract the variance, and then we're going to scale the whole thing by the variance itself. It's a simple formula. Then we're going to calculate the premium standard deviation. Premium standard deviation, which would be just a rolling 6 months standard deviation. And let's run that and see what we have. Now we have the prediction premium. Let's visualize it real quick. So this is the prediction premium, and we have the standard deviation of this prediction premium. Awesome. From now on, we can create our daily signal, right? So our signal daily will be the following. Our daily signal will calculate by doing apply lambda over each row. We have 1 if prediction premium is higher than the premium standard deviation multiplied by 1.5. So 1.5 if the prediction premium is higher than 1.5 standard deviations. Then we have a long signal, or 1. Else, we would have -1 if the prediction premium is smaller than -1.5 standard deviations. And here we have to say the following: else NP none, and then we'll do that for axis equal to 1. We're doing that for each row, right? Let's see what this would give us. This would create this signal daily column. So whenever, you know, the prediction premium is higher than 1.5 standard deviations or lower than 1.5 standard deviations, we get the signal. We may want to explore that a little bit. Equals to 1. We have quite some signals for long, but actually, you know what? We may do the following. We may just plot a histogram instead of, you know, observing the... We want to understand how much short and how much long signals we have. So kind histogram and then POT.show. This would create a histogram, and we'll be able to understand how many. Okay, so what is the problem? Funny. Okay, so now we can see that we have around 50 long signals and then around 35 short signals. And yeah, with that, we are ready with our daily signal, guys, and we can move to the intraday part of the strategy. And here we are going to merge our daily data with the intraday data based on the column, on the date column we have created. Actually, to do that, we will need to shift the daily data one day ahead, right? Because at the end of the 29th, for example, we'll have the daily data, but we'll be using it on the 30th. So we need to do the following up here. we need to say signal daily will be just shifted 1 day forward. That's pretty much what we have to say. And we can move to forming the final date frame. Here we can use our intraday date frame. We're going to reset the index, and then we're going to merge. So dot merge, actually we may move that on the next row. So we're going to merge with the daily date frame, and actually only with the signal column, because we are not interested in the other daily columns. We are interested only in the signal column. We're going to reset the index on the daily data frame as well. And here we'll be using the left on. So left on date, left on this column, and right on date as well, or on the index column, pretty much this one. After the reset, it will be available as a column. And that's pretty much our join. Now we have the 5-minute intraday data, right? And we have the daily signal derived by the GARC volatility prediction. Now we may just want to set the index to be the daytime again, and that's pretty much our final date frame. We can call that final date frame. You can comment that out. Okay, so now we want to drop those two columns. We don't need those two date columns, so we'll say the following: final df dot drop, and yeah, we'll drop date and date. And we are ready now to calculate all the technical indicators potentially we can use for this strategy. To do that, we would need the pandas TA package, which I forgot to import. So we are going to import the pandas TA package. And the first indicator I would like to calculate is the RSI indicator. From pandas TA, we are going to use the RSI method, and we'll just apply the close price. And the length would be 20. Next one is the Bollinger Bands I would like to calculate. So B or lower band first. Here it's B bands. Again, it takes the close price as an argument. However, the B bands are returning 5 columns instead of 1. We have to specify that we want the first column to be returned. So I lock all the rows in the first column. That would be our lower band, and for our upper band it would be the third column: lower, middle, upper. Those are going to be Bollinger Band, lower, upper band. And now I would like to have potentially to use the lags of the lower and upper band, but let's continue without them for now. After we have calculated the indicators, we can just run that part, check out the indicators, and now we can move on to calculate the intraday signal. So signal intraday would be the following. So we'll have a intraday signal whenever the RSI is above 70 and the close price closes above the upper Bollinger Band. So whenever the RSI is above 70 and the price closes above the upper Bollinger Band, we have a burst of momentum upwards or downwards. That's my strategy idea. And this would be our buy signal, and the sell would be when the RSI is below 30 and simultaneously we have a close below the lower bound. This price action pattern is a pure momentum pattern, and we can again calculate it using the apply lambda function. So one, if RSI is above 70 and if the close price is above the upper band. Else we would like -1 if the opposite, pretty much, right? RSI below 30 and close below the lower band. Else we would like to have MP none if those conditions are not met, and the axis will be equal to 1. We can run that and see what we have. We have a small error up here. Why? Okay, so there's something wrong with our data. We can call the info and everything is float. What is the problem here, guys? I found the error, guys. I have forgot to add the X up here for both the upper and the lower bound, and that was doing the error. It's going to calculate the intraday strategy signal as well now, and with that we are actually pretty much ready with our intraday signal and our daily signal, and we can move on now to generating our entry points and our final signal, the final signal that we are going to use to calculate our daily returns from. To do that, we are going to do the following. So final DF, return signal or return sign, that will be the sign of our return and actually the direction of the position. It will be the following. We would have a short position whenever the daily signal is 1, so the prediction premium is above 1.5 standard deviations, high prediction premium. Let me grab that signal daily. So whenever the signal daily is equal to 1 and the signal intraday is equal to 1 as well. The intraday situation is that the price is super overextended, RSI above 70, and simultaneously the close is above the upper Bollinger Band. So I assume a mean reversion, and on the day we know that the prediction premium, the volatility is above the rolling standard deviation or 1.5 rolling standard deviations. Whenever we have those conditions met, we are going into a short position, else we are going into a long position whenever we have the opposite. So both the daily signal and the intraday signal are -1, and else we have MP none, and the axis would be equal to 1 as well. And this would be our intraday signal to get into a long or a short position. Invalid syntax, okay. I forgot the comma up here. Oh, that's not enough. Okay, I'm not sure, guys, what's the problem here, but alright, I think I had forgotten this else. Okay, now we have the intraday signal for each position. My idea here is the following. So whenever intraday, whenever in a given day, we have this signal, the first trigger of that position, we are going into a position and we will be holding for the whole day. So the first time it can be in 10 o'clock, but we can have another signal in the same day at 5 o'clock. We don't care about the second one. We are going into full position on the first one and we are going to hold for the whole day. In this return sign column, whenever we have the first occurrence of the signal, what do we want to do? We want to forward fill until the end of the day the same position sign. To do that, we can use the following trick. Return sign would be, first let's explore what we have. Let's explore what we have so far. So the return sign is our intraday final signal. Wow. Okay. So this one should be 1. All right. So whenever we have to go into a long position, we have long signal. Right here, the return sign. We can observe that this happened at in 2021, 18th of October at 6:05. Then we had another signal on the 23rd of October, then on the 28th, on the 29th, etc., etc. So in some days we may have only one signal, but in some days we may have two or more. We don't care about the second or the third signal. We care only about the first one. So at this point in time, we had the signal, and on the next bar, so on the next 5 minutes, on the open price, we are going to go into a position and we want to hold it until the end of the day. At the end of the day, we close the position. An easy way to calculate the strategy return would be to use just a vectorized return, right? So we're going to forward fill for every 5 minutes after the entry time. We're going to forward fill with the same sign, the return sign column. How do we do that? Final df.group by pandas grouper. We are going to group for every day. We are going to group on a daily basis. We are going to select the return sign, and now we'll use the transform method. And because we have supplied one or MP none, we are able to use the transform method and do lambda x forward fill. And this will now forward fill this value until the end of the day for every day where we have a value. It will be done by the first occurrence of the value. After we run that, we can now select where the return is equal to 1, where we have the entry signal. And as you can see, now we have the first signal at 6:05, 6:10, 6:15, etc., etc., until the end of the day. We can now calculate the 5 minutes returns, shift them backwards with one row for every day, and multiply the return sign column by the signal intraday. Let's do that right now. That would be the following: return percent change, and we would like to get the forward return, right? So forward return, and this would be equal to our return column shifted. We don't need to apply group by daily here because our data is continuous. It's 5 minutes data, but it's from the beginning of the day until the end of the day. It is continuous for every day, including the weekends. And that's why we can just calculate the 5 minute return and then shift it backwards with one row. And our final strategy return will be the following. So strategy return would be equal to final date frame forward return multiplied by the return sign. That would be our strategy return, but it will be on the 5 minute level. So we want to get the daily strategy return. So we'll calculate daily return data frame, and it would be the final data frame dot group by. We're grouping on the daily basis. So for every day, we're going to group by, select the strategy return column, and just sum it. After we have the daily return data frame, we can move on to the final step, and we'll just calculate the strategy cumulative return. That would be equal to expanding window, so numpy expand log, and then cumulative sum, and we just subtract 1 in the end, and we can plot the strategy return. We set the title to be intraday strategy returns. We'll fix the y-axis values to be percentages again. So set major formatter to be from mtick percent formatter 1. The y label, we set it to return. And we're pretty much ready with our graph. And This is our strategy, guys. As you can see, we have an intraday strategy. We may not trade for quite some time. Up here, we haven't traded for almost 6 months, but then we had some trades. And yeah, whenever we have the match of the daily signal and the intraday signal, that's when we are going into trades and we have the returns. That's a strategy using the machine learning model, the GARC model, to predict one day ahead volatility in combination with simulated intraday data. And with that, we're finishing the third project, and I really hope you've enjoyed it, guys. You can find the data and the notebook down below in the link if you're interested to learn more how to backtest quant strategies, how to do algorithmic trading. There will be a link in the description to my website where you can learn more about algorithmic trading and quant trading with Python.